Hi everyone, my name is Kyle, and I'd like to introduce you to our project, Understanding Stress Corrosion Cracking in Stainless Steel Climbing Anchors in a Maritime Environment. Now I'm at the crag, and behind me you can see a climbing bolt with an attached quick draw. So climbers, as they ascend the cliff, would clip into this quick draw with their rope. In case they were to fall, this climbing bolt would save their life. So climbing bolts are very important to climbers, and it's very important that they are functioning properly. Now I have with me here a climbing bolt that's not yet in the wall. It's composed of a hanger, the actual bolt itself, and then a sleeve, which when tightened, expands and holds the bolt in place. So in an environment like Colorado, a stainless steel climbing bolt would take decades to corrode to a point where it would break under climbing loads. Now, in cases in a maritime environment such as Thailand, however, we've seen them fail in a couple years' time. Now, why is this? We'll show in this project that this is due to transgranular stress corrosion cracking. So, in this project, we will begin with some theory on stress corrosion cracking. We'll get into some calculations on theoretically how big a crack there would have to be in this bolt in order for it to fail, and then we'll come up with some recommendations on how we can prevent these failing in a maritime environment. Thanks, bye.
For considering the fracture of stainless steel climbing anchors, there is one particular mode of material cracking that's responsible for this, and that is transgranular stress corrosion cracking. This is a type of stress corrosion cracking that is uniquely chloride induced. So the chlorine tends to break down natural oxide layers that form over metals. Particularly in the case of stainless steel, it's so potent that it overcomes the chromium and molybdenum oxide layers. Because of this, when chloride molecules interact with grain boundaries, they start to corrode at certain points along the grain boundaries, particularly at flaws that already exist in the crystalline structures. This promotes transgranular cracking rather than intergranular cracking, so the individual metal grains fracture themselves rather than just splitting apart. As you might expect, TGSCC is a concern in chloride-rich environments, specifically where stainless steel components are used. Many indoor pools, for example, incorporate stainless steel joists into their roofing structures, and because of the high chloride content from the pool water, those joists are prime candidates for TGSCC. Similarly, in the case of climbing anchors, we see TGSCC affecting those, particularly off the coast of Thailand, where climbers often go because of the unique topography. There are very high chloride concentrations in the air around the ocean as well. So how do cracks actually propagate during TGSCC? Well, when a material like stainless steel is put under a load and chlorides are allowed to continually corrode its microstructure, those corroded regions eventually form crack tips. Those crack tips then start to grow as the corrosion eats away at the steel's molecular bonds, and the applied load further separates the material, which we recognize as further crack growth. Once the cracks have grown sufficiently, the steel will fail. So when we consider environments that are perfect for TGSCC to take place, we see things like roofs over indoor pools collapsing, or climbing anchors failing under the weight of an average person.
Our analysis attempted to determine the critical crack length of failure for the stress corrosion cracking damaged bolts. Our methodology for this included the assumption that the network of many cracks characteristic of stress corrosion cracking could be treated as one singular edge crack of a single effective length. We then followed a form of the strain energy release rate developed by Dawood and Cartwright for this loading geometry, and made several assumptions about the possible range of load conditions at failure, including several different bending moments and several different load cases, including a static and a dynamic or a falling load case. So the results of this are where we run into some problems, namely that the critical crack lengths for many of the geometries we examined are actually longer than the 10 millimeter diameter of the anchor bolt, and the remainder are outside of the crack length to diameter ratio, which the Dawood and Cartwright model establishes as valid. So there are three possible sources of error of this error that we identified, and we'll discuss them briefly. So one, it is possible that the interaction of many cracks in close proximity produced a stress intensity factor enhancement. However, we consider this a low probability explanation because for many randomly oriented cracks in close proximity, the combination of stress intensity factor enhancement and stress intensity factor reduction, depending on the orientation of the cracks, should cancel out to about unity. The second possibility is that the calculations are correct and the critical crack length is actually longer than the 6.25 millimeter limit. However, this does not explain the fact that for some of our load conditions, the critical crack length was longer than the diameter of the bar. And we also cannot be confident in this answer because it falls outside of the model range. So we're left to conclude that the most probable source of this departure between the model results and what is physically observed is that the assumption that many adjacent cracks can be treated as one crack of a single effective length is not valid here.
Alright, first we'll discuss the passivating layer. Essentially what that is a just thin layer of oxide around the surface of steel, and what this does is just protect the base metal from interacting with the environment, so corrosion or just other things that want to interact with that steel. This is what prevents it. When this layer is disrupted or unstable for mechanical reasons, or if any of the corrosive ions diffuse through, you get corrosion like that. Corrosive ions with SCC, they generally actually diffuse straight through the surface like chlorine or sulfur, so that's where you get this internal corrosion that causes the cracking. In this case, the bolts were made of this grade of steel right here. It's generally considered resistant to stress corrosion cracking because it's actually got added molybdenum and reduced carbon content, which reduces the sensitivity with the carbon, and the molybdenum reduces the pitting, increases the pitting corrosion resistance. But in these conditions, limestone was found to leach magnesium and calcium, and these actually form chlorine salts, which then accumulate on the bolts because of the structure of the cliff that they're actually installed in. So these bolts experience extremely high amounts of chlorine, which then diffuse through that passivating oxide layer. Beyond that, they also experienced some acidic conditions which could have affected the results of the studies. The soil runoff from the local soils was inherently acidic, so it actually provided an environment that just was inherently corrosive to the bolts. And additionally, sulfur oxidizing bacteria created an acidic condition by creating acidic cracks because of a sulfide to sulfate reaction that they produced. You could just bypass the issue entirely with titanium bolts. These titanium bolts are actually in use today with glue-in bolts, and they actually don't experience transgranular stress corrosion cracking at all. So it's a much better solution because it just bypasses the problem entirely. But they're expensive because titanium stock is just more expensive than steel by default. And it's hard to manufacture as well because these bolts can't be cold rolled like steel. Titanium doesn't do cold rolling well, and you can't manufacture them on such a large scale as you manufacture steel parts because of that.
In conclusion, we found that transgranular chloride stress corrosion cracking was likely the main contributing factor to the failure of stainless steel climbing bolts in a maritime environment. In addition, sulfide corrosion could have been a contributing factor, but more research needs to be done. Our calculations for critical crack length were found to be lacking with using standard methods. We found critical crack lengths that are unreasonably high, and so more research should be done to better model theory to reality. Finally, we found that using titanium bolts is likely the best solution to prevent stress corrosion cracking in a maritime environment. Thank you.